Okay, distance from motion graphs. You need the paper, which has these graphs on it, and 3 colors. Cut out the paper. Cut dotted lines around every graph. We are going to do these. Okay, so we're going to start off analyzing displacement versus time graphs, which we're going to analyze first. So look at all your graphs that you have cut out. Find the 2 that say displacement. Well, find the one that says displacement versus time. Glue it in, but just put a dot of glue on each corner, the smallest dot you can, because we're going to actually write on that graph. So just a dot of glue on each corner. So if this is a displacement versus time graph, we have time on the x-axis. We have displacement on the y-axis. This could also be a position versus time or a distance versus time, but more traditionally it's called a displacement versus time graph. Okay, so recommend being able to understand these. Little note, this was printed weird. Okay, this right here, displacement versus time graph, where the displacement is equal to 0, that's your reference point. Not that that's terribly important with this, but it might be helpful. Okay, so in this situation, we're starting at the reference point. When we have a positive slope in a displacement versus time graph, it's moving in the positive direction because it's linear, it's a constant velocity. So I like to kind of analyze this like in pieces. Okay, so analyzing this in pieces, this first section right here, we have a constant velocity. Okay, so I'm going to just label it constant velocity. And I'm going to put a positive in front of that because it's going in the positive direction because it has a positive slope. So it's moving in the positive direction. How far did it move? Well, in 2 seconds, it moved 3 meters. So it moved 3 meters. It went from 0 to 3. Okay? This section right here, it's at rest. So if it asks you, how far did it move from 2 to 4 seconds? It didn't move from 2 to 4 seconds. It had a displacement of 0 from 2 to 4 seconds. Just had to kind of pay attention to what it's saying, okay? Right here, we have a constant velocity, but this time it's negative. Negative velocity. Okay, that negative slope, that just means it's going in the negative direction. So instead of going north, it moved north 3 meters, stayed at rest for a few seconds, and now it's moving south. And it moves south past the reference point where it had started, and it kept going. Okay, so from 4 to 9 seconds, it moved from a position of 3 to the reference point, and then 2 more meters beyond it, it moved a total of 5 meters in the negative direction from 4 to 9 seconds. Okay, this is just understanding the graph. There's not any calculations to do when we're doing a displacement versus time graph. It's just paying attention to what the question's asking and analyzing the graph at that moment, in that time frame. Okay, here it is at rest again. Okay, so you could ask, like in this scenario, you could do like 2 questions. You could do like the total distance. Okay, with distance, the direction doesn't matter. So the total distance traveled, be like, okay, I traveled 3 meters, and then I was at rest, and then I traveled 5 meters, and then I was at rest. So it'd be 3 plus 5, a total of 8 meters was traveled for distance. Or you could ask for the total displacement, okay? Which would be asking also for the resultant. Okay, so I started at the reference point and ended 2 meters south of there. Okay, 2 meters in the negative direction. So the total displacement, the resultant, would be a negative 2 meters. Or if that negative means south, it's south 2 meters. If that negative means backwards, it's backwards 2 meters. Like whatever that negative means. Maybe it's down, maybe it's south, maybe it's to the east. It's hard to say, but whatever that negative direction is, it's 2 meters in the negative direction from the reference point. That's the total final resultant. The resultant, where did you end up? 2 meters behind the reference point. Okay? So that is how you do distance, how you kind of read distance and displacement off of those kind of graphs. Just kind of have to analyze it. So that's not much in the way of notes. I'm just kind of like emphasizing it, explaining, clarifying. Okay, gonna do like a little squiggly line here, because now we're going to change mode and change graphs. We are now going to change and do velocity versus time graphs. So in a velocity versus time graph, the slope tells us the acceleration, whereas in the displacement versus time graph, the slope was telling us the velocity. Okay, so you have to kind of like reorient yourself and like, okay, we're dealing with velocity versus time graphs, the slope is the acceleration. There's this really cool trick about these graphs. In a velocity versus time graph, the cool trick is that the distance traveled by the object is equal to the area under the graph. So area, like shapes of an area, like the area of a rectangle, the area of a triangle, the area of a square, okay? That idea of area, the area under the graph, applies to these graphs. It's cool, but let me show you. Okay, so first of all, I need to clarify, do a little refresh, remind. Okay, so we're gonna go to the oops page for a minute. Okay, just to do a quick reminder on some basic geometry. Certain things you probably should have memorized, but maybe in all of the things that they have been shoving into your brain in school, you may have forgotten. Okay, so the first one being the area of a rectangle. So get this little piece of paper that says rectangle. Okay, hopefully at some point in your life, hopefully sometime soon if you haven't gotten there yet, this becomes something you have simply memorized. The area of a rectangle. If I need to calculate the area of a rectangle, okay, it's length times width. Okay, simple way of drawing that area, all right, and I'm going to put a little rectangle shape next to it, equals BH, base times height. So that's the area of a rectangle. Now, triangles are similar. Okay, go ahead and glue that in. The area of a triangle is similar to the area of a rectangle. The formulas are similar. We still need the same information, the height and the base, and we just need half of it. So the area of a triangle is 1/2 base times height. Okay, so the area of a triangle is 1/2 base times height. Now there's a couple ways you can apply that 1/2. You can do area of a triangle is the base times height divided by 2. Okay, my experience is for mental math, it's easier to do the 1/2 base times height because I just take the base, divide it in half, and then just multiply it to the height. In my mind, that's easier mental math. Most of these can be done mental math. Okay, so there is your area of a triangle. Okay, so emphasizing, just a little bit of clarification, whatever the triangle is, you pick a base, you need to get that height You need to have that perpendicular height. It's not the length of the side, it's the height of the triangle. Okay? Now that we remember the area of those two shapes, we're going to apply it to a graph. So take this graph, glue it like in the middle of the page there, evenly spaced. This graph, we're dividing this is the graph, the area under the graph. Okay? We're going to divide it into a triangle, separate it into a triangle and a rectangle. Okay, so with the colors, okay, color the rectangle one color, the triangle one color, and color the rectangle another color. I have a triangle. The area of a triangle is 1/2 base times height. Okay, so I'm looking at this triangle. Its base goes from 0 to 4. Okay, so it has a base of 4 and it has a height. It goes from 0 all the way up to 8. A height of 8. So the area of this triangle is going to be 1/2 multiplied by 4 multiplied by 8. Okay? 1/2 of 4 is 2. 2 times 8 is 16. So the area of the triangle is 16. Okay? Now, it's 16 meters. I'm going to show you the justification of that here in units. There's this thing in physics where you'll hear the phrase chase the units or follow the units. Okay? We just took the base, which is time in seconds. All right? So we did 4 seconds and we multiplied it by 1/2 and then we multiplied it by the height, which is meters per second. 8 meters per second. Okay? Seconds in the numerator, seconds in the denominator. If I have the same units in the numerator and the same units in the denominator, what happens to them? They cancel out. Seconds are eliminated. I'm left with meters. So that's 16 meters. Meters measures distance. Okay? So during the first 4 seconds, this object that was accelerating traveled a total of 16 meters during those first 4 seconds. Okay? Now, let's look at the rectangle. Okay? Area of a rectangle is just base times height. The base of this rectangle goes from 4 to 10. So what's the base of that rectangle going to be? 6. The height goes from 0 to 8. So the area of this rectangle is simply 6 times 8, which is 48. Again, if you follow the units, we multiplied 6 seconds by 8 meters per second. Seconds in the numerator, seconds in the denominator, they cancel. We're left with the unit of meters. 48 meters. So 16 meters is how far it traveled during the first 4 seconds. And then 48 meters is how far it traveled during the next 6 seconds. Okay? So if I want to know the total distance traveled, I add them together. So how far did it travel from 0 to 10 seconds? Okay? So the total distance traveled would be the 16 plus the 48. Thank you. Okay, the 16 plus the 48 gives us a total distance of 64 meters. Okay? Not difficult. You just have to, like with graphs, you just have to be paying attention to what you're doing. What are you looking at? What's going on? Fortunately, it's easy. It's just area. Okay? If you're really good at math, you can kind of piece it together like, oh, I see why it's just the area. If you're not, then just have faith and do it. Okay? All right, now we are going to do this graph. We're going to be writing on it, so try and just put dots of glue in the corners. Yes. This is a graph of motion, so here it's accelerating, and here it has a constant velocity. So while it's accelerating, during those 4 seconds while it was accelerating, it moved a total of 16 meters. And then while it maintained that constant velocity for another 6 seconds, it moved a total of 48 meters. And then we just added those together. The first time I saw this, I was like, what? And I had to sit there and like work the numbers over and over again until my brain was like, oh, that's cool. So if you're kind of like doing that, what? That's okay. More than anything, I want you to see it. I want your brain to start like absorbing this idea, taking this into, account, trying to see if you can process it. You do enough problems and hopefully it'll click. Okay? Okay. So we have a bunch of shapes here. We have a triangle, we have a rectangle, we got another triangle, we got another triangle, we got a rectangle. We divide this graph into multiple shapes, okay? Now, this 3 right here, okay? This is the area of this triangle. Base of 2, height of 3, all right? Base times height, and then half of that gives us 3. So 2 times 3 would be 6, half of 6 is 3, okay? Base times height. So this number right here is the area. It's already written in there. So let's go ahead and make it darker. Okay, the area is 3. It traveled 3 meters during the first 2 seconds. Haha. It traveled 3 meters during the first 2 seconds. Okay, during the following 2 seconds, so here we have accelerating. During the first 2 seconds it was accelerating. It traveled a total of 3 meters while it was accelerating those first 2 seconds. Then we have a constant velocity. And that constant velocity for 2 seconds at 3 meters per second, it traveled a total of 6 meters. From 4 to 7 seconds, so during the next 3 seconds, it returned to the, it decelerated, okay? It decelerated back to 0. So it accelerated up to 3 meters per second, stayed there for 2 seconds, and then decelerated back to 0, okay? So this is a deceleration. While it was decelerating from 3 meters per second down to 0 to a rest, it traveled 4.5 meters. Okay? Now, this person, as soon as they hit rest, they changed direction and started going in the negative direction. So walking in the negative direction, all right, and going faster and faster and faster. So here, it's accelerating in the negative direction. It accelerated for 2 seconds and traveled a distance of 2 meters. And then maintain a constant velocity for 1 second, during which it traveled 2 more meters. Okay? Do you kind of see that? So it's a constant velocity. So accelerating, constant velocity, decelerating, change directions, now accelerating in the negative direction, and then has a constant velocity. So these shapes, all right, we can add up those areas. But you have to notice that this is moving in the negative direction. Okay? So if it's asking for the total distance, direction doesn't matter. All right? How far did he travel? How many steps did he take? Okay? I just add them up. 3 plus 6 plus 4.5 plus 2 plus 2, 17.5 meters. Total distance traveled. Okay? But if I want the total displacement, then I have to take into account the direction. Okay? So I'm going to emphasize here the 3 and the 6 and the 4.5 were all moving in the positive direction. We'll say they're all going north. But these two values for 2 are going in the south, are going the opposite direction. Okay? So we need to subtract -2 and -2. Opposite directions. So if I take 3 points, so if I add these up, that's 13.5 minus 4, 9.5 meters was the total displacement.